Hey everyone, Mr. Miliano here. We are going to be talking about doing work with a piston. Our end goal of all of this is to understand a little bit about how engines work. So we'll start with looking at the big picture and then we'll start zooming into some of the particulars. So on the left here, we have an animation of a four-stroke engine. We can see that the yellow here is intaking gas, then we compress it, then we ignite it, then we exhaust the spent fuel. And we repeat that over and over and over again. Our goal for the next couple of videos is to understand this action inside of that cylinder to understand the piston. And so you can see where he got a piston here, and we're using that to drive a rod. And that rod is connected to some sort of rotational device that can then give us rotational motion, typically to turn a wheel in a car or something like that. Some vocabulary on the right here for the schematic, the part that's moving up and down there, that's what we call the piston. The connecting rod, the crank bearing are not necessarily a part of what we're going to be talking about here, but you can know what they are. And then the walls there are the cylinder. So we've got the cylinder and the piston are the two parts that we are talking about. So I want to start by looking at people pushing on the piston inside and outside of the cylinder. And those people are going to be an analogy for the gases that are involved in maybe that connecting rod. And so we've got the cylinder here. This is the outer part is the cylinder. And we have this piston here. And we've got this person, Bob, inside of the cylinder. He's going to represent the gas in the cylinder. He'll be what we'll call the system later on. And then on the right, we have Alice. Alice is going to represent anything outside of that cylinder. So the atmospheric gas outside of the cylinder, maybe that connecting rod, or anything that might be pushing up against the piston from outside of the system. And we can have Bob win the fight, and Bob pushes harder than Alice, and that strokes the piston outwards. Or we can have the other reverse happen, where Alice pushes and wins the fight against Bob, compressing the gas inside of that cylinder. So here's the analogy. We've got sort of a grid we're going to set up with an initial and final snapshot, and we'll start looking at some of the words and the language that we use to describe these things, because the language can get a bit tricky. So there's our initial snapshot. We've got a piston, we've got Bob and Alice pushing against that piston. The final snapshot for this first scenario we're going to look at is the case where Bob wins, where Bob pushes harder than Alice. When that happens, here's how we describe it. We might say that Bob gets more tired. He pushed harder than Alice did. And so the work is done by Bob. Or another way to say that is that Bob does work on Alice. Those prepositions are going to be key in the way that we talk about what's going on. So the work is done by Bob because he won, or the work is done on Alice because she lost. Let's look at the other scenario, where again, the initial snapshot looks very similar, but now the final snapshot is when Alice wins over Bob. In that case, we would say Alice does the work. The work is done by Alice. She wins, she gets more tired than Bob, so the work is done by her. Or the other way to say that is that Alice does work on Bob. So that's the way we're going to talk about these things, but we're going to replace Bob and Alice with gases inside and outside of the system. So let's move our picture away from people inside of our cylinder, and let's look at actual gases now. So there's our initial snapshot. We've got the red gas particles that are zipping around in there representing the gas in our system. We are defining the system to be the gases inside the cylinder. And the blue gas particles here, those are any gas outside of our system, but it could also be any other things outside of the system. But for simplicity, we'll just look at it as being the atmospheric gas. Let's look at the first case scenario where the final snapshot is the gas inside of our cylinder expands. It pushes that piston such that the piston moves to the right. The verbal description here is that the work is done by the gas in the system, or we could also say the system does work on the surroundings. Let's look at the other possible scenario. Our initial snapshot looks identical, but now let's look at the case where the atmospheric gas outside of our cylinder wins and pushes that cylinder to the left, compressing the red gas inside of the cylinder. Here we would say that the surroundings won, so the work is done by the surroundings. Another way to say that is that the surroundings do work on the gas that's in the system. So be careful about which gas we're talking about. We're talking about the gas in the cylinder, the system, or the gas outside of the cylinder, the surroundings, also called the environment sometimes. And then be careful with your preposition on or by, talking about who is doing the work and who is receiving that work, receiving that energy. So let's look at an example problem. We'll look at Bob and Alice first, and then we'll move into gases, because we know how to deal with work done by people pushing with constant forces, but what determines which gas wins the fight? So we'll look at an analogy we're familiar with first, and then we'll move into the gases. So we've got Bob, and he pushes the piston with a constant 3 Newton force, displacing the piston 2 meters to the right. How much work does Bob do on Alice, the Alice piston system? So we're moving it 2 meters to the right. So our picture, this is our initial snapshot. Our final snapshot looks something like this, where that piston is further to the right than where it was before by 2 meters. And let me move my talking bubble here. The work that's done is going to be the force times the displacement. That's our definition for how much work is done. And the force is a constant 3 Newton force, and the displacement is 2 meters of displacement, so the work overall ends up being 6 Newton meters of work. Pretty straightforward application of our definition of work from earlier. Now, how does this translate to gases? Because the force that the gases do is sort of a complicated combination of all of the gas particles that collide against that wall. So let's look at this. The system maintains not a constant force anymore, but a constant pressure of 3 pascals, increasing the volume of the container by 2 cubic meters. These are very unrealistic numbers, but it does make our math easier as our first example. So how much work does the system do on the surroundings? So here's our initial snapshot, sketching out the system, and the picture is always your first step. Here the piston moves to the right because the volume of the container increases. And so now this is something with a greater volume than before. And we're going to do a little bit of math manipulation here. So the work is still going to be defined as the force times that displacement, but we are given neither force nor displacement. So how do we change that formula to work with the quantities that we're given, pressure and volume? So we've got work is force times displacement. What we're going to do is multiply by a clever form of 1. We're going to multiply by area over area, the area being the cross-sectional area of this cylinder. So if we divide force by area and multiply displacement by area, hopefully we can see that this expression is mathematically equivalent to force times displacement. This is a helpful expression though, because force per area, that's our definition of pressure. And if we take the cross-sectional area and multiply by how much linear displacement there's on that piston, you're going to get how much the volume expanded, how much change in volume there was. And so we get work is also equal to pressure times change in volume. Don't write down this formula, don't box it in yet. There's going to be a small caveat in a second. But right now, this works for us. That's going to be 3 pascals of pressure multiplied by our 2 cubic meter increase in volume. And we're left again with 6 Newton meters of work. And this work is done on the surroundings by the system because the system won that fight. The gas expanded. So let's generalize this a bit. We're going to look at graphical representations and sort of 2 parts here. So first, for a constant force, notice that caveat for a constant force. For a constant force, the work done by that force is the force multiplied by the displacement. We can represent this by finding the area under a force versus position graph. So let's move over there. All right, so there's our graph. Force is on the vertical axis, position is on the horizontal axis. And let's look at the example from the previous slide. We've got a constant 3 Newton force, and that happens over a displacement of 2 meters. And we said the work was that 3 newtons times that 2 meters. Visually, 3 times 2, that can be represented as that area of that rectangle. So the work done there is 6 Newton meters. Now, let's look at the identical or the analogous thing for a gas with a pressure changing its volume. In this case, for a constant pressure, the work done by or on the system is the pressure multiplied by the change in volume. Displacement was changed in position. We got the volume change now. We can represent this as the area under a pressure versus volume graph. We're going to abbreviate these graphs as PV graphs or PV diagrams. So here's our graph, pressure versus volume. And the example from the previous slide, we had a constant 3 Pascal pressure. And this volume change was an increase in volume of 2 cubic meters. That's going to matter here, that is an increase in volume. And so again, to find that 6 Newton meters of work that we found before, we can find the area of that rectangle, the height of 3 pascals multiplied by the base of an increase of 2 cubic meters. And we end up with a work of negative 6 Newton meters. I'm going to talk about that negative sign now. This was an increase in volume. So by convention, when the volume expands, we are going to say that the working that is done is negative. The working by the surroundings is negative because it's the thing that's getting tired. It's losing the energy to the surroundings. It's pushing harder. We are also, when we start drawing these PV diagrams, these PV graphs, we're going to give the curve, the purple line here, an orientation, which means we're going to give it a direction. The volume wasn't compressing 2 cubic meters, it was expanding 2 cubic meters. And so we're going to have this direction arrow, this orientation from left to right because the gas was expanding. So when the gas expands, that will be negative working by the system because the system is getting tired, it's losing the energy to its surroundings. So that was for a constant force or a constant pressure, but it turns out that this process generalizes. So you can always use the area under a force versus position graph to find the work that's done, even when that force is not a steady constant value. So if you have a graph like this for your force versus displacement, something where the force is increasing as you move to the right, it is still true that this area is going to be equal to the work that's done. Similarly, even when the pressure is not a steady constant value, it is going to be true that the work that's done by the gas is the negative of the area under an oriented pressure versus volume graph. Negative because as we expand, the gas is getting tired and losing energy, and oriented because we're going to care about, is it the gas that wins and expands the piston in the cylinder, or is it the surroundings that win and the gas actually compresses? So here we're going to put our orientation arrow, shade in that area, and the work is the negative of that area. So that is the end of this video, talking about how do we find the work that's done by a gas for pressure and volume, and talking about pistons and the pistons moving inside of the cylinder.